All right, today we are diving into a rule that honestly runs just about everything. From the steam rising off your coffee to the engine in your car, it's all governed by the first law of thermodynamics. We're going to get to the bottom of what temperature and heat really are to understand one of the most basic, fundamental ideas in all of physics. So you've probably heard this a million times. Energy can't be created or destroyed. It's a famous rule, right? But if that's actually true, where does it go? I mean, when you boil a pot of water, you're pouring energy into it. When a car engine runs, it's using up energy. It kind of feels like it just disappears. Well, the first law of thermodynamics is what solves this exact puzzle.
You know, at its heart, the first law is really just an accounting principle for energy. It's that simple. It says that the change in a system's internal energy, that's the delta E sub int, is equal to the heat you add to the system, that's Q, minus the work done by the system, which is W. It is the universe's ultimate unbreakable budget.
To make this super intuitive, let's just think of it like a bank account. A system's internal energy, that's your total account balance. Any heat you add, the Q, well, that's a deposit, money coming in. And any work done by the system, W, that's a withdrawal, money going out. So the first law is just saying that the change in your balance is, well, it's your deposits minus your withdrawals. See? It's that straightforward. Okay, so let's break down the parts of that equation. And we'll start with Q. What is heat? We use the word all the time, but in physics, it's got a super specific meaning. And here's the key. It's not something an object has. It's energy that is actively moving. It's literally energy in transit. So here's the formal definition. Heat is the energy that moves from one place to another only because there's a difference in temperature. Energy just naturally wants to flow from something hotter to something colder. That actual flow is heat. So, in our bank analogy, this means you can only get a deposit of heat from something that's hotter or at a higher temperature than you are. But wait a second. For this whole idea of heat transfer to even make sense, we need to be able to trust our measurements. I mean, how do we really know our thermometers are telling us the truth? For that, we need a rule that's so fundamental, so basic, that they actually had to call it the 0th law of thermodynamics, because they came up with it after the first and second were already famous.
And this is it, the 0th law. It sounds a little complicated, but it's really simple. It just says that if two separate things, let's call them A and B, are both the same temperature as a third thing, our thermometer T, then A and B must be the same temperature as each other. It's basically the if A equals C and B equals C, then A equals B rule, but for temperature. It's the simple but profound reason we can trust our thermometers.
Okay, we've got the deposit, Q, covered. Now let's talk about the withdrawal, the work, or W. In thermodynamics, work is usually about a system pushing back against its surroundings. It's about expanding or getting compressed. It really is the energy of expansion.
And this is the absolute classic example. Just imagine some gas trapped inside a cylinder with a movable piston on top. If you heat that gas up, the little molecules inside start flying around faster, and they push harder on that piston, forcing it to move up. By lifting that piston, the gas has done work on the outside world. It has spent some of its energy. It's made a withdrawal from its energy bank account.
Now, physicists love to visualize this stuff, so they plotted on what's called a PV diagram, which just shows pressure versus volume. And here's the really neat trick. The total amount of work the gas does is just the area under the line on that graph. A bigger area means more work was done. Simple as that.
And this is where it gets really interesting. You can go from your starting point to your ending point in a whole bunch of different ways, right? You can take different paths. And the path you choose actually changes the area under the curve. This means that both the work done, W, and the heat added, Q, are what we call path-dependent. The amount of each one depends on the journey, not just the starting and ending points.
So wait a minute. If the deposits, Q, and the withdrawals, W, can be different depending on the process, how can we possibly have a consistent law? This brings us to the most important piece of the whole puzzle, the internal energy, E ent. This is our grand total. This is the actual balance in our bank account.
So what is internal energy? It's the sum total of all the little energies of all the countless atoms and molecules bouncing and jiggling and vibrating inside a system. But here's the magic. Unlike heat and work, the change in this internal energy does not depend on the path you take. It only cares about where you started and where you ended up. That makes it what physicists call a state property.
And this is the absolute beauty of the first law. Even though Q can change and W can change depending on the path, their difference, Q minus W is always the same if you have the same start and end points. It's constant. And that constant value is exactly the change in the internal energy. So no matter how you shuffle your deposits and withdrawals, the change in your final balance is locked in.
Okay, theory is great, but let's make this real. Let's see how all these pieces, Q, W, and internal energy, come together in a super common example, just boiling a pot of water. So here's what happens. First, we add a whole bunch of heat, Q, from the stove. Now, this doesn't actually make the water hotter. It stays right at 100 degrees Celsius. Instead, that energy causes a phase change. The liquid water turns into steam, and get this, it expands like crazy. 1 kilogram of water goes from a 1-liter bottle to filling over 1,600 1-liter bottles. This massive expansion does work, W, because it has to physically push the air in the atmosphere out of the way. And finally, the internal energy of all those H2O molecules shoots way up as they break free and start flying around as a gas. So, where did all that heat energy we added from the stove actually end up? Well, this chart breaks it down. A tiny little slice, just about 7.5%, was used to do the work of pushing the atmosphere away. But the vast majority, over 92%, was pumped directly into the internal energy of the water molecules themselves to make the phase change happen. I think this is just a fantastic takeaway. When you boil water, you're not really just making it hot. You are mainly just pumping huge amounts of energy directly into the microscopic state of those water molecules. Only a tiny fraction of that energy actually does any mechanical work on the world around it. Kinda wild, right?
Okay, to wrap things up, let's zoom back in on Q for a second. How does heat actually get from point A to point B? Well, it turns out there are 3 main ways it happens. The first one is conduction. This is just heat transfer through direct touch. The atoms at the hot end of something are vibrating like crazy. They bump into their neighbors, which makes them vibrate, and they bump into their neighbors, and so on, passing the energy down the line. It's like a microscopic chain reaction. It's exactly why the handle of a metal spoon gets hot if you leave it in a bowl of soup.
Second is convection. Now this one happens in fluids, so liquids and gases. When you heat up a fluid, it usually expands, gets less dense, and starts to rise. Then the cooler, denser fluid sinks down to take its place, and you get this circulation, this current that carries heat with it. This is the engine that drives our weather, ocean currents, and, yep, the bubbling in that pot of water we were just talking about.
And third, we have radiation. This is energy moving in the form of electromagnetic waves, like light. What's crazy about radiation is that it doesn't need any stuff to travel through. It can go through the total vacuum of space, which is exactly how the sun's energy gets to us. And as this incredible thermal image of a cat shows, pretty much everything that has a temperature, including you and me, is constantly radiating heat energy out into the world.
So let's bring it all home. The first law of thermodynamics, it's not some weird new rule that came out of nowhere. As the source text says so well, it's really just taking that core principle of energy conservation and extending it, applying it to real-world systems that aren't isolated, systems that can actually exchange energy with their environment through heat and work.
And that leaves us with one last really big question to think about. If the first law is true, if the total amount of energy in the entire universe is fixed and can't ever be created or destroyed, then why in the world do we have an energy crisis? Why are we always told to conserve energy if it's already conserved by a law of physics? Well, that's a fantastic question, and it's a puzzle that the second law of thermodynamics starts to unravel. Thanks for joining.